In this video, we are going to explain the paper Teaching StyleGAN to Read, Improving Text-to-Image Synthesis with U2C Transfer Learning. In recent years, many novel deep network frameworks to deal with this task have successfully been implemented, and these architectures are also rapidly evolving. To address the problem of artificial image synthesis, GANs have emerged as architecture with promising results, and recently diffusion models as a generative framework that synthesizes image with high variability and trustworthiness. The generation of image based on detailed natural language descriptions is an even more difficult task, as it inserts the representation of natural language into the problem. GANs are able to learn from a large amount of image. However, text-to-image models depend on high-quality labeled data that is scarce. Transfer learning is a known technique that alleviates the need for labeled data, though it's not trivial to turn an unconditional generative model into a task-conditional one. We introduce unconditional to conditional transfer learning, U2C transfer for short, which allows the use of pre-trained information from an unconditional network to generate task-conditional image. It is able to leverage pre-trained models that generate human faces and adapt them to synthesize high-quality images of birds and flowers, for instance. So, this transfer learning technique uses a different domain of an unconditional model as a source to a different target domain conditioned to test. Such images do present fine-grained details that respect the input textual query. This method not only stabilizes the training process, but also makes the convergence faster. Note that it is challenging to train a task-conditional model on these datasets, given that they present a rather limited amount of image, which the discriminator easily overfits. It is also complex to get proper textual representation that contain rich details regarding the data distribution of the dataset. With few examples of captions, the space of the sentence representation is highly discontinuous, highlighting the need for a better design for such encoder. U2C transfer is tested in the standard StyleGAN 2 unconditional models by fine-tuning them in two widely used but limited datasets. The resulting model, a text-conditional StyleGAN 2, effortlessly bests prior work results using U2C transfer in a few hundred iterations. We use the maximum number of pre-trained weights as possible, make only indispensable changes to the architecture. Such adaptation is not trivial, since the model has to take an additional vector which dictates the natural language condition. That has to be done without causing the collapse of the pre-trained model. For that reason, we believe that the modification should be minimal and added in the right place with parsimony. TC StyleGAN 2 makes use of strategies to prevent overfitting and to increase the smoothness of the embeddings. We also demonstrate that TC StyleGAN 2 enables image editing using natural language through arithmetic operations not only in the conditional space, but also in the intermediate mapping space W, being able to modify several aspects of the image like colors, size, and some specific details. We show it that W space carries a meaningful and learned representation of the sentence. Now, we are going to talk about the few modifications that we proposed to StyleGAN 2. It is not restricted to StyleGAN 2, and we strongly believe that these modifications could be extended to other GANs architectures. Our synthesis network takes two input vectors, the noise Z and the test unconditional vector S. Such vectors are concatenated and then mapped to an intermediate representation W through 8 layers of a nonlinear mapping network F. Given that we adjusted and projected the input vectors into the regular dimensionality, it is possible to load trained weights for the entire generator G and F. Note that Z follows a certain probability density and S is a pre-trained embedding space. But the intermediate latent space W can learn a more linear, less entangled representation, since it does not have a previously defined distribution. The discriminator can take either a real image or a generated image. Such image is processed by several convolutional layers that output discriminator latent representation D. In parallel, we input the conditional vector S into a new randomly trained mapping network that operates in the 256-dimensional. We then employ a linear projection layer E to generate S hat, which is a 512-dimensional vector. We use such linear mapping so we can get the same representation level and disentanglement from the intermediate space of the generator. Then, we compute a similarity score cosine between S hat and D to encourage the discriminator D to approximate the condition distribution. The final output from the discriminator is the weighted sum of a neuron and the cosine score. The weights are lambda c, that represent the conditional weight, and lambda d, the unconditional weights. So both values have weights while detecting if an image is not only real but also correspondent to the natural query. Hence, our two largest modifications are splitting the input vector from the generator and this introduction of a new randomly initialized mapping network that is parallel to the discriminator MEM network flow. Such network mainly adds a constraint to the prediction and does not affect directly all the discriminator layers. We observe that we can get away with both modifications because they do not impact strongly the main flow of the network, though provide additional learning signal. The test descriptions were encoded using the Deep Attentional Multimodal Similarity Model D8MSM from the Attention Gun Encoder model. In order to increase the continuity and smoothness of the space of the embeddings, we employ the condition augmentation technique proposed by the authors of StackGAN. The default incarnation of TC-SAGN2 uses ADA, which proved to be important in unconditional to conditional transfer learning, that allow us to fine-tune large models in small datasets while maintaining generalization capabilities. For most of our experiments, we use the StyleGAN pre-trained weights on Flickr face data to initialize the discriminator and the generator weights in the new architecture. Some layers have to be randomly initialized, such as the mapping network and the linear projection of the conditional vector employed in parallel to the discriminator. We employ the standard dataset for evaluating test image synthesis, namely CUBE, the birds, and Oxford, the flowers dataset. This table provides an ablation study that shows the impact of each component in the generated design of our method. The models trained from scratch had the worst results, and sometimes the training procedure diverged. ADA clearly caused strong reductions in the feed score. It's very clear that U2C transfer does bring important improvement to the results. Text augmentation improved performance on the CUBE dataset, while for the flowers dataset, the results decreased marginally. This table shows quantitative results for our main approach, the TC-SAGN2, as well as results from prior work. Notably, our approach outperformed all past work by large margins. We achieved 7.48 feet in CUBE dataset. Note that TC-SAGN2 results present a relative improvement of roughly 40% when compared to Lafitte. Compared to previous reported feed results for Oxford flowers, once again our results are second to none. The training from scratch results in more training stability after few iterations and may cause divergence. The left figure illustrates how the fine-tuning in the first iterations already reached a reasonable value of feed, but this is reversed as the training progresses. Using ADA, the fit will take longer to improve, but model gets far more robust to overfitting and instability. Using the complete approach, ADA and fine-tuning, the transfer learning results in the state-of-art feed values very quickly. The rightmost image shows that our method outperforms most of prior work in a few hundred iterations. TC StyleGAN tool is also capable of editing image in the textual space while preserving structural and main features of the birds and flowers by doing arithmetic operations in text embedding space. The learned intermediate space W has structural regularity. This figure shows that interpolation between distinct input condition embeddings, but with the same noise, we can observe a gradual merging of features between the generated image as requested by the prompted test query. To summarize, we introduce a new simple and effective transfer learning adaptation technique that using an unconditional model for training test conditional GANs. We also added strong augmentation recipes and strategies which allow us to train reasonable large models in very small datasets. We have shown that pre-trained information of an unconditional model trained in a different and more diverse dataset is really helpful when training in smaller datasets. Our model outperformed previous SOTA models by large margins in terms of feed in widely used benchmarks and took only a few hundred iterations to top most of the prior work. The learning procedure was more stable when using the proposed strategy, and our model is capable of image editing by using arithmetic operations and also interpolation in the latent intermediate space of the mapping network.